Example 3. What if the variable is in the lower limit? So up to now, we've looked at integrals where they've been the integral from a number to a variable, and the variable has been in the upper limit. Now I'm going to show you what to do if you have a variable in the lower limit. So we're going to look at a couple examples that are this way. So in example A, we want to determine dy dx. So the problem here is that our integral is from x to 5 and not 5 to x. Well, we're going to use an integral property that says that you can switch the limits of integration if you put a negative sign in front of it. Okay, so now we fixed our problem. So now all we need to do is take the derivative with respect to x to both sides, and you get dy dx is equal to the derivative of negative the integral from 5 to x 3t sine dt So then using the first fundamental theorem of calculus, we get that this dy dx is going to be equal to negative 3x sine of x. Now note, I did not use the product rule. You only use the chain rule and use substitution when using the fundamental theorem of calculus. The product rule does not come into play, you simply just replace the variables. So now we're going to look at a next example where we have a variable in both the lower limit and the upper limit. So the trick here is to get a constant or a number in the lower limit of the integral. So we have dy dx, taking the derivative of both sides, is equal to d dx, the integral from 2x to x squared, of 1 over 2 plus e to the t dt. So again, the problem is we don't have a number in the lower limit. Well, I'm going to use an integral property to show you that the derivative can be written as, then, the integral from 2x to 0, 1 over 2 plus e to the t dt. Now the 0 came from, it was just a number I chose. It could have been 5, could have been 6. I chose 0 because it's a nice number. Using the fundamental theorem of calculus, we don't really care what the lower limit is as long as it's a number. And yes, I know it's the upper limit. We're going to fix that in a second. Plus the integral from 0 to x squared, 1 over 2 plus e to the t dt. Now what we need to do is fix this first integral so that the constant is on the is in the bottom. So you get d dx, the integral from 0 to 2x by putting a negative in front, 1 over 2 plus e to the t dt, plus the integral from 0 to x squared, 1 over 2 plus e to the t dt. And remember back from the derivative properties that derivatives do distribute. So then you're going to take the derivative of both. So using the fundamental theorem of calculus, I'm going to take the 2x and put it where the t is. So I get negative 1 divided by 2 plus e to the 2x times the derivative of 2x plus 1 over 2 plus e to the x squared times the derivative of x squared. So here I'm going to get the derivative of 2x is going to be 2. So 2 times negative 1 is negative 2. Divided by 2 plus e to the 2x plus the derivative of x squared is 2x divided by 2 plus e to the x squared. So this is dy dx. And that is your final answer. Okay, let's move on to the last example. I want you guys to try this on your own. Try to determine dy dx by using a couple integral rules and then the fundamental theorem of calculus. Alright, let's see if we got it. So the first thing I'm going to do is I'm going to rewrite this integral with a negative so I have a 0 in the lower limit of integration. Okay, now that I have that, I can go ahead and just apply the fundamental theorem of calculus. So I get y is equal to, or dy dx is equal to d dx, the integral from 0 to x cubed of tangent the cube root of t dt. So I get dy dx is equal to negative tangent the cube root of x cubed times the derivative with respect to x of x cubed. So my final answer is going to be negative 3x squared tangent, and the cube root of x cubed is simply just x. And that is your answer.